start recording, share screen, and get straight into it. So this is Tute 8, and that's, sorry, push. My internet's being really slow. Okay. Tute 8. So the first one is about generics. Let's talk about what generics are and why we use them. You probably all know what parameterization is. You may not know the exact term, but you've all definitely used it at some point. Does anyone want to take a stab in the dark at what is parameterization and why it's useful to us? To kind of go to maths, I guess, if you have like a vector in parametric form, what does that look like? I've forgotten this from, yeah, here we go. So you essentially have a vector, right? And you have these parameters R, S, and T, right? And you can say, well, I'm going to say R equals 1, S equals 2, and T equals 3, kind of like, you know, like config files. So parameterization just says, I'm going to pull out some variable and make it this arbitrary parameter. Okay, you think that's pretty cool. And you think, well, that makes sense when we talk about functions, because functions have parameters. You're like, okay, public string hello, string message. Right, the parameter here is message, in that we can substitute any string in for message and you know, print it out or whatever it's doing in this case, return another string. That's all good. What if we wanted to do something like what if we wanted to say, maybe I've got this, you know, a function which is like public something, maybe just like a print function. And the problem is, it's like, well, okay, we'll write we'll say public string print and then take in a string. You know, message. And you go, oh, but I don't just want to print strings, I want to print integers as well. So, okay, let's write an integer one. Public integer print integer, you know, blah, blah, blah. Okay, let's do one for doubles and one for objects, maybe. The problem, as you all know, is there's an infinite number of possible classes in Java. What do we want to do here? Before, when we wrote this function, hello, we said, okay, I'm going to parameterize the message string. That can be anything the user of the function wants it to be. It can be hello, it can be hello world, it can be 1, 2, 3, 4. So we parameterize the object. But here, what do we want to do? We don't just want to parameterize the object, we want to parameterize the type. And that is what generics allow us to do. So I guess we'll continue with this example here, and I'll just write up code is like, go to stack. You know, your function in this case looks like public T, and T can be anything. T can be a string, T can be an int, T can be a, I don't know, Dungeon Mania controller. We don't care. And we'll say print, and this takes in an object of type T. We'll call it message. And we'll just say out.println message. And if you actually go to the print statement definition, I haven't done this, but it takes in an array of characters, takes in a string, takes in, this one actually just takes in an object, right? Because everything is an object. So I guess you could just write an object definition. This is probably a bad example for how it would actually work, but the essential idea is, as you picked up on, is we want to parameterize the type. And it's giving us this red line here because we need to say there's this thing which we haven't exactly defined. We've define this parameter called t, and then that will go away. Oh, sorry, I need to return message as well. Does that kind of make sense? So now, semantically, we can say, well, what if I can define a type, right? This is just a function. What if I wanted to define a type, like a stack, for example, and you think, well, I don't really want, I don't want to have a separate class like a stack of strings and a stack of integers or a stack of stacks. We don't really want that, but then we also don't just want a stack, because under the hood, you're going to need to, maybe under the hood, our stack is just an array list, which is like, elements equals new array list. And you're like, oh, well, object, what's the problem with this one? Yeah. Yeah, it's like Python. You're just like, let's have a list of a string and an int and a double and a 1, 2, 3, 4. It's like it's like who cares? But you still want to constrain the type of a particular instance. You want to say, here's a stack of strings, here's a stack of integers. But we don't have to make 10 classes. So what we can do in this case is parameterize the entire class on this unknown type E. And E can be anything. That's the first thing. That's essentially what generics are and why we use them. And you've been using generics the whole course, right? Whenever you create an array list, any sort of list, array list, map, the list kind of goes on and on. And you said, I'm going to have a list of strings, list of integers, and under the hood that uses generics. We're going to learn how to define our own generic types, we can see here. So that's what E is. What's the iterable interface? Why does it need to have E as well? What methods does it force us to implement? I just want you to look at this code and, to the people you're sitting next to, briefly think of the answers to these 3 questions. I'm going to try and bring them up together. So what's the iterable interface? Why does it have an E as well? And what methods does it force us to implement? You got about a minute and a half. All right, any thoughts? What's the iterable interface? Yep. David. Do you want to say it again? Yeah. So something that's iterable, you can loop over or you can iterate over, which essentially means you can put it on the right-hand side of a for loop. Okay. Why does it have an E as well? What's this about? Yeah, you're on. Yeah, it's like you'll be, so you have a stack of E and then you're going to iterate through the stack of E, and so you'll be iterating through E's. Cool. And then what methods does it force us to implement? Let's have a look at this one. Does anyone want to take a guess before you start? Really? Not quite. not stream, but you're on the right track. Anyone? Which method here is the one we've been forced to implement? Iterator? Yeah. Let's have a look. So we go to definition and you can see we're forced to implement the iterator interface, sorry, the iterator method, which says, given a stack, an array list, whatever, return an iterator to that object. We'll look at iterators more in a second. All right. Let's start coding this thing up. Let's get my stool. So, okay, we've got a stack, but how does it actually work? Well, you know, there's lots of ways we could do it, but probably the easiest is just to make our stack a wrapper around an array list. So it's just an array list under the hood, but we've got these nice abstractions like pop and peek and push, which allow us to treat it like a stack. And the user of the stack obviously doesn't know that it's just an array list under the hood. It could be anything. So we'll start with an empty list, I guess. So we'll say public, oh, it's public, private, list E, elements equals new array list E. And again, this is where the actual composition comes in this parameterization, is you have a list of type E elements. And that is what your stack consists of. All right, so these functions are pretty simple. So what can we do to push something onto the stack? Yeah. Elements, sorry, elements.add element. And you can see because the signature of the function is E element, and this matches the type parameterization of our list, we can just push it on. Why don't we need to, you know how before down here, did I get rid of it? I think I got rid of it. Why don't we need to say what E is in the function? Yeah. Yeah, and under the hood, actually, it does it quite interestingly. But essentially, because we've defined what E is at the top of the class, it's like E is defined for the rest of the class. So when we talk about E, we're talking about the same thing. And at runtime, that will be a string. It will be an int. Depends on how we instantiate it. There's a super interesting kind of set of concepts around how this works under the hood. And it's what we call, like, you know, we talked about dynamic polymorphism back in week 3 with inheritance. This is static polymorphism. I don't know how exactly it works in Java, but in languages like C++, what it does is it actually creates, like if you create a stack of strings and a stack of ints, it will create in memory a custom definition for, like, and do what David said, where it's just strings put in the place of E's. Like this E isn't real. And then there's a stack of ints and they're two custom like classes. That's not core or important, it's just kind of interesting. But essentially the idea is, yeah, we have this E which is consistent throughout the class. All right, so now we've got pop, precondition, the stack is not empty. What can we do here? We take the top element off the stack. Yeah. Oh, sorry, dot remove. Yeah, sorry, that's the first. So we'll say element. Well, actually, before we do pop, maybe let's do peek, because then we can say get the element, and then maybe let's remove it. So what should we do for peek? Yep. Oh, sorry. Yeah. And then what can we do here? Do I need to do anything else? I think we might be missing something. Yes, let's pull it out into last equals peak and then remove the last. This kind of also, I guess, is another precondition of the whole stack is like you can't have the same element more than once because then you just remove the element. I don't know how this, whether it removes like the first one. Yeah, it removes the element with the lowest index I, so then you wouldn't actually be removing the last element, you'd just be removing the first object of that, you know, where the equals is the same. But it doesn't really matter. This is fine. This is, you know, other than that problem, good design because you're piggybacking off an existing method. Yes, Sonny? Because we need to return it. Because that's like when you pop something off the stack is like you remove it from the stack, but you also give it back to the user. So this will be fine. This is bug prone. Cool. Let's do size. This is easy. Anyone? Yep. Okay, to array list. So we're going to return the stack as an array list. What should we do for this one? Okay. What's the oh, sorry. Oh, I need to just typecast it. What's the problem with this approach design-wise? Yeah. No, it's okay. The type's all consistent here between these two. If you think about, you know, what our stack's trying to achieve, right? You know, we've made this stack class and it's just a wrapper around an array list, right? Like these are, you know, these are 1, 2, 3 line code changes. And they allow us to treat it meaningfully like a stack as opposed to just, you know, any plain old array list. But if we just say, well, you know, you say, okay, I want to convert this stack to an array list, like that's a pretty reasonable request. But then you just say, here's the actual internal structure of how the stack works under the hood. What's the problem with that? It starts with the word starting with E. We can play Hangman again if you want. Anyone? Okay, Hangman it is. I feel like you're gonna get like 2 letters when you get to the okay. Next one. Yeah, there we go. See, I was like, you know what it was. Encapsulation. Why is this bad encapsulation? Yes, and what's the problem there? You can change it. It's like you've made this whole big abstraction around the stack, but then you say, "Oh, give me the array list." Then they might as well just have the array list to begin with, right? Because you've just given them. Remember, this is a pointer, and they can modify it. They can just, you know, add in, you know, remove elements at will, and that will change this stack itself because, you know, Thorpe's pointers. And so, like at that point, it's like you've given them the keys to the castle. So what's the whole point of having a stack class in the first place? Does that kind of make sense? So what's the solution then? We still want to give them an array list. We just don't want to give them our array list that we have storing the elements under the hood. Yeah. So we'll just make a copy. So we'll say new array list. I think you can do this. Yeah. I think that works. This is like a copy constructor where you pass in the original object to a new constructor. I can't remember. I don't know. I feel like this might not work, but conceptually it's like you want to make a new object, whether it's like you actually just have to make a brand new empty array list and then copy over the elements one at a time and stuff, which is just a bit more cumbersome, but you get the idea. Right. So we've done this one. All right, the iterator method. Let's look at the test in stacktest.java. Oh, we've got all these tests. That's so lovely. I should have run these. So we've got this stack of strings, and you can see again, we've got this instantiation of different generic types where it's, the stack of string, and then down here we've got a stack of ints. At the moment, if we run this test, the test fails. Why? Because null pointer exception, right? This is happening under the hood, but it's trying to iterate through, or it's trying to use the iterator to iterate through the stack, but at the moment we return null. And that is what an iterator is. So we've got this idea of an iterable, which is something semantically that can be iterated over. And then the iterator allows us to do the iteration itself. So it's like, here's your thing, your stack or your object. And then you have a method called iterator, which returns this little kind of iterator thing. You can have as many iterators as you want. Here's 1, 2, 3, and they can be different types of iterators as well. I talked about this in the lecture on Monday, but there's some design ideas around why you want iterators and to essentially abstract the traversal of the object from the object itself. But the iterator is just a pointer, which says, here's my stack. Give me the next element, and then it increments this little pointer. It says, okay, now I'm going to point at the next one. You keep giving the next one, giving the next one, and eventually you get to the end and the iterator runs out, and this one runs out, and so forth. So here, when we make a for loop, sorry, this code's not well formatted. This gets an iterator under the hood and works its way through the iterator until it finishes, and that's what a for loop is. So in our stack, what do we want to do? And remember, we've said our stack is iterable, but array lists are also iterable. So is there an easy way we can kind of palm this off without having to do it ourselves? Yes, but we don't even need to typecast. We can just say return elements dot iterator, because that's going to return an iterator as well, and it's also going to return an iterator to an object with type E, like we have there, because our array list has E, and yeah, so our list has E. That implements the iterator interface because you can loop through that, right? You can put that in a for loop. Sorry, I've lost my spot. Here we go. So we can just palm it off. We don't even have to worry about it. Does that make sense? Cool. So now if we run this test, save this test, it still fails. Okay. Why might it be failing? We've returned the iterator, but we're defining a stack here and how the iterators work. Yeah. So iterator says, give me the first one, give me the next one, give me the third one, blah, 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 keep going until the end. But for a stack, remember, it's like a stack of plates where you take the top one off first, which is the most recent one you put on, then the next one, then the next one. So the first one that got put on is the last one to come off. So what should we do here? Yeah, reverse it. So we'll make another copy. Actually, what we'll even do is just say list E equals copy equals array list to array list, and then we'll say copy dot reverse. No, how about this? Collections dot reverse. Here we go. Copy, and then sorry, CP, and then we'll return copy dot iterator. And now that should work. What's the problem with returning the original, with reversing the original and then returning it? Yeah, it's like you don't want to reverse the whole thing. You don't really want to reverse it. You just want to return the iterator to a reverse copy of the list. Cool. Now let's run all these. I think they should all pass. Oh, this one fails. Oh, we haven't implemented it yet. Okay, so the next part is utility functions and more stuff with iterators. So a utility function is like something that's part of a class, or it's sort of attached to a class in a way, like it's kind of related, but it's not part of the original definition. So in this sum stack method here, it's like this is a piece of functionality which is to do with stacks, but is it part of every single stack? No, how come? Yeah, it's like your refused request or your not LSP, but it's like an inheritance postman where you say, well, you know, all stacks have this certain. It's like the you know, animals have legs, a chair has legs, so a chair is an animal. It's like a chair's not an animal. Yeah, so here this only applies to stacks of integers. And we can still make this piece of functionality. We can still even put it in a class if we want to, but we'll have it as a separate static method. And what we will also do is use generics to allow us to constrain the type. Where are we? Here we go. No, sorry, this one. Does anyone want to take a stab in the dark at what this syntax means? Yeah, so it takes an integer. What does this extend mean? We've seen that before, right? Does it mean the yeah, exactly. So it has to be integer or anything that extends integer. It's like a, you know, if you think about less or greater than or equal to, you know, here's that integer class, and then you know, maybe you have 3 other classes that implement it. Not that there are. And this wildcard means integer or anything below it in the hierarchy, anything that extends it. So okay, that's cool. How can we change our class definition? Let's actually do this one first. Yeah. Yes, it's like this is like a greater than or equal to semantically, I guess. Does a class extend itself? I guess so. Yeah, I think that works. So what does that mean then? Well, I guess we can do a typecast in that case. In fact, no, I don't think we even need to do a typecast because we have the type constraint already. So what we'll say is int total equals 0. And then for integer element in stack, say total, actually, let's do this properly. What we'll say is int total equals stack dot stream dot reduce. I might have done this badly. Stream. Oh, that's annoying. Sometimes you encounter weird things with generics like this, and let's just do it the easy way. Total plus equals element. I tried to do the streams a bit nicer, and then we'll just return total. And we don't even have to do any typecasting because we know that the type is parameterized on something that must extend an integer, which means we can do this without any type checking. So if we test that now, it should work. Yep. The next question is, well, what does question mark super type mean? This is a wild card, by the way, this question mark. What does something super type mean? And again, we've seen the word super before. Yeah. Opposite the first one in that. Yeah. So you know, here's integer. So I can take integer or anything above that in the hierarchy. So any superclass of integer. So if we really wanted to, we said, well, actually, our stack only can contain integers. What would we change this to? No. I'll show you what happens if you do. The type parameter integer is hiding the type. Oh, this is like you've overwritten it. So it's now like it's namespace stuff where you just like overwritten variables. So that's not great. But it's not that. You can do something else. Yeah. I'll show you what happens if you do question mark extends integer. Because see what the problem is now. Right? We haven't defined E anymore. But what we can say is E extends integer. So where there's this thing E, and all stacks created have to extend integers. And if we go to our stack test, these are all going to break now because they're like, well, oops. Come on, before. Here we go, bound mismatch. The type string is not a valid substitute for the bound parameter, saying, well, you don't meet the criteria. And notice this isn't a runtime error. This is a compilation error. So this is all done statically. Okay. Let's change that back to the test pass. Now we want to do the last one, which is pretty print. And what do we think this means? Could be anything, right? Like wildcard in. I don't know what wildcard's from. Now, the other thing with this function is we could actually say, if we wanted to, we could say like stack, I don't know, not say E, but what about T, right? A stack of any type T. And now we have to, because we're in a function, say, well, we have this undefined arbitrary parameter T. Publics, sorry. Maybe say public static T. There we go. But this is only if we want to use T anywhere. We want to say, okay, maybe T first equals stack dot pop, right? But we don't actually need to use it in this function. So we can just say, we don't even need to define a type variable. We'll just say, yeah, there's a stack. We don't know what's in it, but we don't really care. And what we'll do is stack dot for each element system dot out dot print line. Cool. And then we'll run that, and it should print it out. And notice because, oh, sorry, I'm actually on this. Notice because we're using the iterator, it will print out in the correct order, right? So you say you are out. Cool. Oh, I see. They wanted us to do it a certain way. The other way you can do this is using an iterator, where you say iterator E equals stack dot iterator. Sorry, iterator question mark. Again, we can use the question mark here because we don't care what it is. We call this iter, and then we'll say while iter dot has next. Print the element, and we'll say, oh, yeah, this is a bad example actually, now that I think of it, because you need to declare some sort of variable. So ignore this, don't worry about it. Are there any questions on anything to do with generics? Because that's pretty much it. This is pretty cool. I really like generics. You know, get into like type theory and all this interesting stuff. COMP2511 discusses like the ideas behind generics in a lot of depth. So that course runs next term if you're interested. Yeah. We use generics a lot in like software engineering as well. You won't see it a lot in your project, but there are a few labs on it that you'll understand the motivation, and probably like even just from this example, you kind of understand why we use generics. And also the fact that you've been using them all along. If there aren't any other questions, let's crack on straight to the next one, which is about the Singleton pattern and concurrency. So we have a bank account and we have an integer called balance. Pretty simple, balance equals 0. You can deposit stuff in the bank. You can withdraw from the bank. I'm just going to move this. And you can get the balance. All right, cool. So now we have this accessor, which is you can think about it like when you go to the, not the, oh, when you go to the ATM, you say, well, I want to access my account, that's here. And this is like you standing at the ATM. So you go to the accessor and say, can I please access the bank account? They go to the bank account, withdraw money, blah, 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 return you some stuff. But what we have here also is a thread. Sorry, I'm just looking at my computer on fast. We also have this thread, this threaded accessor object, which creates a new accessor and then does a withdrawal. But the problem is we create 3 accessors, and now things start to get a bit weird. And this is the world of threading and parallelism and concurrency. This is just a main method, so like don't get too confused by like why is this part of the class. But essentially we have 3 threaded accessors, which is just an accessor that runs as part of a thread, and you can see that this class here extends thread. So what we have is the way I like to think about it is like a race. I don't watch the F1, but a bunch of my friends do, and it's like you've got here's the start line, and then you've got all your cars, which in this case are the 3 threads. Right, we've got Rio, Tokyo, and Denver. So here's thread 1, here's thread 2, here's thread 3, and then the sort of racetrack is the code that needs to be executed. And what we want to do is we want to run them all in parallel, which means they all run at the same time. So when we say start, this one starts. Then we say, and then what happens is this goes and runs this run method. But instead of it being sequential, and we return to here once this is finished, it actually goes, no, you just go off and do your thing. I'm going to keep going in the background. So this goes off and runs, this goes off and runs, this goes off and runs. And because computers are all really fast, this all happens like that. And there's very minimal time between reaching this line here and the next thread starting. So you've got all these threads which are moving towards, moving through the code. And what are they all doing? Well, they're all trying to access the bank at the same time. So if we run this now. Oh, I think we put a sleep in there just to kind of make it more manageable. So the balance is $1. I think it's really hard to produce the race condition here. But if you think about it, what's going to happen if you have multiple processes all trying to access the same piece of shared data? Let's do this in green. Old mate here is trying to access it, and old mate here is trying to access it as well. What kind of problems might we get? Yeah. Yeah.
Just before you
yeah. Mm. Yeah, exactly. So, and the thing about with any sort of operations at lower level, of course, like OS or 152, you'll appreciate that, like when you go balance minus equals amount, like there's a lot going on in that process. And so each individual step is being executed by the JVM or the kernel or whatever it is. And because of that, you can have things occur between, not within the same line, multiple threads. So as Sonny just said, we could have, maybe the account balance is 10, right? And so, person one, person one, person two, person one reads it, x equals 10. Okay, now we're going to withdraw $20 or $5 or $1 from it. So we're going to write it back as x equals 9. But the problem is, while you were busy reading it and setting the new variable, this person came along and went, okay, well, x is also 10. Now I'm going to take $2 off it. X equals 8 now. So thread 2 goes and says, well, actually x equals 8, and then puts it back in. And they got there first. And then thread 1 comes back along and says x equals 9. And so what happens is x equals 9, right? It's like the Google Docs problem of the first bit, like you got two people and they both uploaded a document to the Google Docs, and one person got there first, and so they were first, and then the second person overwrote the first, right? And Google Docs is supposed to solve that. And this is called the race condition. And you can hopefully appreciate why. And it arises when multiple processes are trying to access the same piece of shared data. So what's the solution? Yeah, so we don't go into like the full ideas of concurrency with like locks and semaphores and mutexes and all this wild and crazy stuff. What we really care about is, well, okay, I want to stop this thing happening here where we get this, reading and writing crap going on. I want to say only one person can access the bank account at a time. And we do that using this thing called synchronization, which Java provides support for. So what I will do here is in the accessor, we're going to make this synchronized, and we use the singleton pattern. Okay. How we do the singleton pattern? Does anyone know what the singleton pattern is? No? A singleton is single, one. So you can only ever get one instance of it. Which means that if you say, okay, give me, like most objects, you can have as many instances as you want. But we want to say, no, I can only get one because only one person can access the bank account at a time. How might we do that? It's like, how do you keep track of instances for a particular class? Yeah, statics. So we're going to say public static get instance. And then we'll implement that later. And what we'll have here is a private static bank account accessor instance. So this is storing statically an instance of the class, right? The only instance of the class, because it's a singleton. What do we want to do here? So someone says, okay, give me a new instance. Give me a new bank account access. You say, well, one of two things should happen, right? Either I've already got an instance, you can have that, or actually I don't have an instance, let's make a new one. So we'll say if instance equals null, instance equals new bank account accessor. Oh, we need to pass in the account. Yep, pass in the account, and then we'll say return. Oh, actually, we just do that. Otherwise, return instance. Sorry. So if someone comes along and says, give me a new instance, and you've already got one, you say, here's one, you can use that. But if we haven't, then we give them a brand new thing. Yeah.
Why don't we just put like 16?
Yeah, you could do that. I don't think it really matters. You think that's great. What's the only problem, if you look at the rest of the class, what's the problem here? And think about kind of what we talked about last week with constructors and encapsulation. What's the problem with this? Sorry? It changes. No, the constructor is the same. But what's the problem with its access level? It's public, which means that even though you've got all this fancy get instance stuff, if they don't call the get instance method, that doesn't work. And so someone can go and create a new accessor and give it a bank account and it'll still be the same as before. So all we need to do is just make this private, which means we can access it from inside the class because we still want to use it here. We still want to use a constructor, but we don't want other people to use it. Cool. So now, obviously, this is going to fail because the constructor is not visible. So we'll say bank account accessor dot get instance. And that all works. Now, the last thing we need to do is to do the actual synchronization because this is just a singleton, right? This is just saying here's only one instance, but we need synchronization to mean that only one thread can operate on the data at a time. And to do that, we just say public synchronized. And it spells it like an American. We could put the synchronized in a bunch of places, by the way, and in lab 8, I'll show you how to do it in a second, actually. But what we do is we synchronize the entire method, just because I think in the spec, it says, yeah, only one person can access the bank at a time. So they do a bunch of withdrawals, right? You can see that from the output. And it should do all the withdrawals for Rio, then all the withdrawals for Tokyo, and blah, blah, blah. You could synchronize, we'll do that in a second. You can synchronize different parts. Let's run it again now. And you can see that only Rio is accessing the bank, and then that's finished, and then the next person accesses, and then the next person accesses it. There'd probably be an even, so if let's say you wanted to just synchronize the write to, where is it? Sorry, I missed it. The write, this one, this here. And generally you want to synchronize as little code as possible. So we could just say public synchronized Boolean, blah, blah, blah. Obviously, that means that multiple people can still access the bank, but you don't have race conditions anymore. So I haven't actually tried this. Let's run it again. It'll probably just be the same as before, I think. The balance is a bit more now. Yeah, the behavior is a bit weird, and it's not consistent as well, which is why you get concurrency bugs that are flaky. So it's like you might have a test that picks up a concurrency bug, but it only fails half the time or a quarter of the time. And if we wanted to go even more granular, and I'm just showing you so that you see the syntax, is we put the synchronized around this block where it's like synchronized this, and then that code block there is synchronized and everything else is fair game. And to kind of give one more like conceptual illustration of what synchronization means is that, you've got your three, maybe these are three runners in a cross-country race. And they're all starting on this big open track, right? So this is runner 1, runner 2, runner 3, and they're all going. And then eventually you get to a part where the path becomes constrained, right? And it means that they have to go in single file. So there's 1, or 1, then 3, then 2, or whatever order that they work in. And it means they go in a sequential order. It means they go in a queue. And that's essentially what synchronization means, to force it to do it one at a time. Any final questions? No. Cool. I will stop sharing and